Hi, everyone. Welcome. This is the Oracle Autonomous Database Learning Lounge. I am Marcos Anasivia, part of the product management team for Autonomous Database. And today we're going to have a very, very cool session on spatial AI. So how to actually supercharge your apps with spatial intelligence in Autonomous Database. So today we're going to have David Lapp. He's a senior principal product manager. He's going to be talking to us about spatial AI and how that actually brings all that capability for the Autonomous Database, and actually that running inside the Oracle Machine Learning for Python. So we're going to see that. He's going to be talking about how the spatial AI actually improves machine learning models accuracy. And also he's going to be doing a demo, right? Demonstrating that, how to enhance home value predictions using basically the capabilities of spatial AI, all right? So throughout the session, we're going to have Q&A. If you guys have any questions, please type them in the Q&A section in Zoom. We have Oracle product managers looking at your questions, and they're going to be answering those. We're going to be distributing to you guys links in chat. And the recording for this session is going to be made available right at that link, bit.ly/ADB-learning-lounge by the end of the week, okay? All right, so these are some of the important links for Autonomous Database for you guys to bookmark. I'm sharing them right now with you in the Zoom chat, okay? And please take a look at that. And so, things like, join us in social media or even in developers, right? So in the developer Slack, we have an Oracle developer Slack channel. So a workspace, so you can join us and find the Autonomous Database channel right there, okay? All right. So again, thank you for joining, guys. And I would like to thank David for joining us today. I will stop sharing and let you start sharing your screen. And again, thank you, David, and take it away.
All right, thanks, Marcos. All right, well, thank you for that introduction and the polls. That helps. I'm going to do an overview of some really exciting new capabilities on ADB, as Marcos described, around basically harnessing the value and power of location and location relationships within the context of machine learning. So this is OML4Py, Oracle Machine Learning for Python, Spatial AI, and this is all about bringing the capability of location-based predictions and pattern detection to ADB-S. So folks are on the Autonomous Database Learning Lounge. Folks are familiar with what Autonomous Database is, but just to get these critical sort of acronyms out of the way for anyone that's really coming in new, I'm going to be talking about Oracle Machine Learning for Python. That's OML4Py. And that is our Python environment, Python API platform that basically brings machine learning to the Oracle database and Oracle Autonomous Database. Full machine learning lifecycle lets you sort of live and breathe and work in your comfort zone of machine learning environment, machine learning notebooks, et cetera, but behind the scenes, you're really working and leveraging the power of the underlying database, again, while working in that sort of Python comfort zone. And in this particular case, we're going to be talking about Autonomous Database Serverless, which is, as I expect most folks are aware of, is Oracle's fully managed, autonomous, self-securing, self-scaling, self-patching autonomous database service. So those are the acronyms that are going to come up over and over here. And what sort of in the big broad sense, what this is all about is being able to take advantage of location in machine learning for predictions and pattern detections. Things that are done currently, if you work in OML4Py, you're doing lots of prediction, creating models for predictions and detecting patterns and trends. And what we're here talking about today is the ability and value in bringing location into the fold. And so actually, before I sort of take the next step here, I'm going to show just a quick bit of what this is all about very quickly up front here. So I'm going to just log into my OML environment in my own OCI account. So I've got an ADB-S environment, and this is the OML UI for that ADB-S environment. And this has been around for a while now. Very mature, powerful, full environment for machine learning workflows. So what's new here is the set of spatial algorithms and spatial features that let you take advantage of location in this context. And so one quick and easy way to sort of discover some of those capabilities is through the set of example notebooks that come sort of bundled with OML. And you can find those from the homepage by clicking examples. And these have always been around, and there's lots and lots of great example notebooks for OML and OML4Py that demonstrate all kinds of essential functionality. They generally start with a notebook where you get the data loaded and set up, and then all the rest of the notebooks show you how to do all kinds of interesting things that you'd want to do, everything from aspects of data exploration, data preparation, applying different and creating different sorts of models and so forth. So that's been around. What's new here is if we put into our search filter spatial. So now we have, amongst all these sample notebooks, a whole array of sample notebooks for this new spatial functionality. And just like the rest of the sample notebooks in OML, one of those notebooks is one called Run-me-first. And that's the one that seeds all of the data, gets all the data loaded and configured, which is then used by all the rest of the notebooks. So, this is the notebook that you run to get the data set up. And then from there, it's sort of open season. So any other notebook can be run in any order based on what your interest is. So all kinds of functionality. And I'm gonna in a moment go back to PowerPoint, sort of give you the overview of what all this capability does and how it works. But just wanted you to see that this is all like there now and available for you to play with if you have an ADB-S environment. So just as an example quickly of what some of this stuff would look like and what sort of the point of it is, we have an example for hotspot, detecting hotspots, sort of hotspot clusters. And I'm just going to open one of these as an example to give you a general sense. When you click on these sample notebooks, you're opening them in a read-only fashion. So this is just so you can take a browse through a pre-built, pre-run notebook, see what it does. I'll show you later how you can take those sample notebooks, make a copy of them into your own project as a read-write, fully editable notebook that you can play around with. But just to take a quick tour of one to show you where all this is going. So each of these notebooks sort of describes what this particular piece of functionality is. We're looking for hotspots and cold spots for income in the city of Los Angeles. So each of these notebooks will describe the sort of the concept here, which in this case has to do with the concept of finding hotspots and cold spots from geospatial data. Libraries will be loaded. I'll talk more about this in a moment, but critically, what we do is we create a data frame in Oracle Machine Learning that's really just a proxy and pointing to spatial data in Oracle Spatial in Autonomous Database Serverless. I mean, that's really sort of a cornerstone. So we're now working with spatial data in an OML4Py Spatial DataFrame. And what we do in these notebooks is generally sort of explore the data, talk about what the spatial ML algorithm is that we've added to OML4Py that we're going to work with for this particular exercise. In this case, it's a hotspot detection algorithm. And we will run that algorithm, label the data, and eventually have a result, which in this case is showing us where are the hot spots and cold spots for income zoomed in on a particular area, all based on applying one of these new spatial ML algorithms that's baked into OML4Py on ADB-S. And then, of course, all this gets persisted back to Autonomous Database and then could be used downstream for other purposes. Whatever other aspect of the workflow is talking to Autonomous Database now knows about where the hot spots and cold spots are for, in this case, income. All based on a set of sort of parameters and thresholds that were set within the way that this particular model was fit. all the details aside, the details really don't matter right now. All that matters is I just wanted you to see that this is one example of this whole sort of wide and deep portfolio of spatial algorithms and associated features that are now part of Oracle Machine Learning for Python on ADB-S. So now that you've seen just a quick sort of sneak peek of what I'm going to talk about, now I'm going to sort of introduce all this stuff a little more formally, and then I'll jump back into Notebook and run through a couple of other things. So just to sort of set the stage, I think most folks hopefully are aware of the fact that Oracle Database has had native spatial capability for over 30 years now. The native spatial capability in Oracle started in the Oracle 7 era, became a real sort of production-ready feature in Oracle 8i, and has evolved with great acceleration over time, and is an extremely mature capability. So the ability to store, manage, process, analyze geospatial data natively in Oracle Database, that's not new. That's very mature. And it's supported across the geospatial industry. All the tools and platforms that work with spatial data support our Oracle Spatial platform. So these are the kinds of things that Oracle Spatial does. Store geospatial data like points, lines, and polygons. See examples of what that kind of data would represent. And by the way, in addition to that, Oracle Spatial manages and supports a whole variety of other geospatial types. 3D data, LiDAR collected 3D point clouds, geospatial imagery. There's a whole bunch of other stuff, but for the sake of this conversation today, we're focusing on the basic geospatial data like points, lines, and polygons. Historically, and what we've done for a long time and do really well in the database is answer the kinds of questions we see on the right. And those are questions about explicit spatial relationships, questions that are sort of explicit questions about spatial measurements and computations. What items are inside a region? What's the nearest item to a location? What's the area of overlap between regions? Those are explicit questions that we can answer natively in the database. It's not new. Here's what's new. So what's new is that same Oracle Spatial in the database, every Oracle database, including Oracle Autonomous Database, has that capability. And so now we're with our spatial AI features in OML4Py, we're now answering a new class of questions that have to do with machine learning, pattern detecting things and predicting things. And so you see on the right a few examples of the kinds of questions that we're now able to answer using the spatial AI features in OML4Py. So the sort of the brain there, the fact that those questions are pointing up to that brain icon is because that's where spatial AI in OML4Py lives in OML4Py, but is sitting on top of and interoperating and working on data that's in the Autonomous Database. So that's sort of the broad view of sort of what's new here. So before then getting into sort of what are the features and what are the specifics about what spatial AI offers, it's first, I think, important to understand the scenarios that our spatial AI features are designed to address. And in general, you have probably already inferred that what these new features I'm talking about are built to address are really scenarios that involve some type of, we'll say, some type of location effect, some type of behavior of your data, or behavior in what you're trying to detect or predict that relates in some way to location. And if there is no relationship whatsoever to location, then of course we wouldn't be adding value in those cases. However, there are lots and lots of cases, more than you'd probably guess at first blush, where there are location effects that are sort of explicit or maybe hidden that aren't necessarily intuitive, but they're there. And in those cases, these spatial algorithms that we have provide value by finding things you couldn't otherwise find or predicting things better. So these are four of the sort of the most common examples of these so-called spatial effects that our platform is designed to address. And I want to just sort of make sure that these are somewhat clear, and a little bit of the jargon, I want to get out because the jargon can get in the way sometimes. So I think hopefully this explanation here of the scenarios that we address is hopefully, pretty intuitive. So just to drill into one for a moment, the first and a pretty intuitive one, I think, is a scenario where the feature or the variable or the value that you're trying to predict is influenced by the values of that variable amongst its neighbors. So, for example, if you're going to use machine learning to predict the value of a home value sale or the value of a Airbnb rental, let's predict what this value would be. Well, that's a common machine learning exercise, and there'd be all kinds of features that would help you in that prediction model training. How many bedrooms, how many bathrooms, is there a nice yard, is there a deck, is there parking? All those sorts of things have predictive value and would go into be incorporated into a model. Where we come in this particular scenario would be, is the value of the neighbors of the neighboring houses, do those values actually have a predictive influence of a value you're trying to predict? And commonly the answer would be yes. So you take the same house that is for sale, and you surround it with a bunch of very fancy houses, and you take that same house and you surround it with wasteland. There's a predictive influence related to what is surrounding the thing that you want to predict. That, in terms of jargon, is something that's referred to as spatial dependence. And that really has to do with the correlation, if you will, between a value at a given location and the values of that same variable in the surrounding locations. That's one of this list of sort of spatial effects that are often inherent in the data that you're working with. So that's an example of the kind of spatial effect where, when that is the case, so if we take predicting home values, for example, if the data are sort of analyzed and the data are put through some statistical algorithms, those algorithms can detect whether this spatial effect is in fact exhibited by the data. And if that's the case, then the prediction algorithm that we apply will take that into account. And that will result in just better predictions because we're including more intelligence in the predictive model. In this case, the intelligence to say that it's important not only how many bathrooms and whether there's a deck and a view, it's also important to look at the sort of the surrounding value of houses. And you can see several other examples of other sorts of spatial effects that we are out to address. So what you'll see throughout the rest of this presentation, when you think about spatial AI and OML4Py in general, really, I would say think about it in terms of when the data exhibit any of the sort of the spatial effects that are location related, then there is value to be had. You can find things you wouldn't find otherwise. You can make better predictions, more reliable predictions by leveraging these algorithms. So that's the sort of the conceptual idea of sort of what this is all about and a little bit of when it comes into play. So now, from the standpoint, sort of the actual footprint of this thing, where does it live within the stack, and what all does it contain? So the first thing, which I think has already been made pretty clear, is that this is not a new separate product, Spatial AI. This is really a set of algorithms and related features that are built into and part of OML4Py, Oracle Machine Learning for Python, and specifically Oracle Machine Learning for Python on Autonomous Database Serverless. That is where it lives. and that's the only place that it lives. This isn't one deployment or configuration option. There is nothing to deploy or configure. If you have Autonomous Database Serverless, you have Oracle Machine Learning, you have OML4Py, it has Spatial AI baked into it. It's not something that can sort of separately be downloaded and deployed on premises or as part of any other environment. This is really something that is for ADB-S. And again, no separate licensing, configuration, anything. It's just there. And because it's part of OML4Py, it allows you to do all the things I'm talking about within the mainstream workflow that is what OML4Py users and developers are used to. So in other words, it's not a set of features in OML4Py that really has its own notion of everything and just happens to be living under the same roof. No, it sort of shares the same sort of the same approach and the same sort of framework of the rest of OML4Py. So that includes working, as you've already seen briefly, working in OML notebooks and OML projects. It has the same basis, this fundamental basis of this notion of proxy data frames, which is so fundamental, so important. And what that means is that you as a Python developer, data scientist, are working in your comfort zone of Python notebooks, working with data in data frames, not with SQL and tables and views. You're working with data frames. But those data frames are really just proxies and references to underlying data in Autonomous Database. That's a cornerstone of OML4Py, and we, as part of OML4Py, we're part of that. And as you can see, I've listed a few of the other sort of foundational aspects of working in OML4Py that we are sort of jointly designed to leverage. So that's sort of where it lives and what to expect in terms of being a user. In terms of the main set of features that I've just sort of bulleted out into these 4 main categories. So just to have a quick view of sort of what all is contained, what does Spatial AI and OML4Py contain? Well, the 4 things that I'll call out are, first of all, sort of starting from the top left, what I've said here is Python API for spatial SQL operations. And what that means is, before we get into anything that has to do with sort of ML algorithms per se, we have included in Spatial AI the ability to work in Python and have one of these proxy data frames to spatial data in the database, and have methods on that data frame that allow you to do common spatial operations like point and polygon and within distance, and those types of things that you commonly need to do for example, if you want to explore your data and get a sense of spatial relationships. That stuff is very mature and people know how to do that with SQL, but this is OML4Py. So what we've done is we've created these methods that you can apply to perform common spatial operations, and those actually proxy out and invoke behind the scenes spatial SQL in the database. So the point here is that as a Python person in OML4Py, you can do a within distance operation in Python with a Python method and not have to know the SQL. And you don't have to open a SQL paragraph and do SQL because that's not your wheelhouse. You want to work in Python. So that Python API for these common operations is sort of an important starting point. And that's really part of, I'd sort of consider that part of a pre and post processing area, which is the second item. So again, before getting into the prediction algorithms and all that stuff, there's commonly, almost always, some degree of pre and post processing. And there are spatial specific algorithms and features that we've added there. The first would be, of course, using that API I just mentioned for feature engineering. I've got a set of houses and I want to create a predictive model for value. And maybe for every house, I'd like to add a new feature, which is the distance to the nearest train station, or how many libraries are there within 5 miles. Well, that first Python API for SQL I just mentioned is what you can use to generate those sorts of features and do spatial feature engineering. And then there's other aspects of pre-processing, like filling gaps in data. which is a common thing that you need to do. And there's algorithms for doing that that when there's no spatial involved, we'll just replace missing data with a sort of a total summary of non-null values. Well, we have spatial algorithm to fill gaps in data, but basically using a spatial context so that you're filling sort of missing data with location-specific values. And what I want to take a moment just to talk about with pre-processing is this thing called spatial weights and spatial lag. And that's really super important everywhere, because a big part of, as soon as we get into the algorithms on the right, a big part of what those algorithms include, and a big part of what they incorporate, is when we're trying to detect things and predict things at a location, we commonly want to know, well, what's going on in the neighborhood of that location? What's going on in its surroundings? That's the spatial context. And that spatial weight, spatial lag thing, that's just more jargon. But the jargon aside, what that really means is the formal definition of what we mean by a neighborhood and what we mean by sort of the aggregate value of something in the neighborhood of a location. That's a real fundamental sort of cornerstone of a lot of those algorithms. And that's something that's part of our pre and post-processing set of features, is to define all that. Then the real meat of what this is about is what's on the right, the spatial ML algorithms that are, all the algorithms that address pattern detection and predictions. And then I've called out on the bottom right spatial ML pipeline specifically for the Python developers, the data science people who work in scikit-learn, which is the super popular, pervasive library for data science. And one of the really common ways, and the most common pattern for using scikit-learn and assembling, creating a model that it sort of assembles a bunch of different steps that do different sorts of maybe pre-processing and estimating something and filling gaps and then applying some algorithms. And a scikit-learn pipeline is the way that is commonly done. And that's so common that what we've done is taken that scikit-learn pipeline and we've enhanced it to be able to accept and include our spatial algorithms, our spatial estimators. So our spatial estimators can be included as steps within our spatial ML pipeline, which is just sort of an enhancement of the scikit-learn pipeline. If that's not something that's important to you because you're just dipping your toe in the water, you can just ignore the stuff I said. But for the folks that sort of live and breathe these scikit-learn pipelines, I think would be a very welcome message to know that holds here. Then I am, not to go through these in detail, but we just wanted to include more of an enumeration of specifically what are the algorithms in those categories that I mentioned previously in terms of pattern detection and prediction. So, cluster detection, anomaly detection, different regression models, classification models. These are specifically the algorithms that are in this first release, this V1 of Spatial AI and OML4Py. And this is going to grow, and this is going to become more and more robust. But this is what is in there today, and this is copied right out of our user guide. And I'll be providing the links to the documentation where all this stuff is described in more detail. And maybe this is just an opportunity to take a breath for just a second and mention the fact that this is V1 of Spatial AI and OML4Py. These are the algorithms. I just mentioned that there are going to be more algorithms added as we sort of determine the priorities of what people need most. And I'll also mention that I said before how this is all about point line polygon data, what people have commonly referred to as spatial vector data. There's a whole other side of the coin when it comes to spatial AI that has to do not with point line polygon data, but a whole side of spatial AI that has to do with so-called raster data or imagery data. And that has to do more with things like detecting objects detecting objects like cars and buildings and forests from satellite imagery and so forth. That's a really other big, important, critical area of spatial AI, and that's actually something that is sort of in the works and is part of our strategic roadmap. So just to sort of zoom way out for a moment and sort of look at this in context. But again, coming back to what's there today, I'm going to continue on now with what you see here.
David, while we're on the topic of V1, Ariam has the question of whether the functionality also includes spatial temporal analysis already, and whether you even have a piece of sample code or something. Do you want to quickly comment on that?
Yep. That's a great question. And the answer is, when I said that we are adding to this, and there's going to be more algorithms added, that's a perfect question to ask, because that question, that's like right at the top of our list, is to add at least one spatiotemporal algorithm that we've already identified and worked with and so forth. So the answer to the question is spatiotemporal is not in there right now, but it's absolutely in our short-term roadmap for these sort of spatial vector algorithms. It's also on our longer-term strategic roadmap in terms of spatiotemporal in the sense of change detection, being able to see and identify how things have changed in like satellite imagery over time. So, answer is it's not there right now, and it is there both in terms of short and longer-term roadmaps. And we're really very glad to hear and would welcome any specific feedback on a particular model or algorithm or requirement, just so that we can fold that in and make sure that it's part of what we're already planning.
And David, there was an interesting question here about the algorithms themselves. Someone asking whether these algorithms are known in the industry or they are unique.
Great. Thank you for asking that. And I'm remiss in not having made that clear. So these algorithms are sort of almost all they're all based on industry standard, known, published, well-adopted algorithms. In a couple of cases, we've taken those well-adopted, known algorithms, and we've made slight sort of enhancements to them or made them slightly more robust, for example, maybe so that they return some additional statistics or metrics that the original published algorithm didn't, and we've sort of added some methods to them. But the answer is that everything that we see here are well-known, well-adopted algorithms. And so the main thing that we're bringing here is not inventing a new set and a new class of machine learning sort of algorithms. It's really about taking these state of the industry, state of the practice, well-adopted algorithms and allowing you to use them on Autonomous Database in OML4Py in this fully managed service, as opposed to having your own Python environment and pulling data out and loading your libraries and wiring everything together. Here, it's all baked together. So that answer actually extends to the fact that not only are these well-adopted algorithms, like a spatial lag model, spatial error model, these are known terms in the industry. Spatial AI in OML4Py actually incorporates and bundles some extremely popular, well-adopted open source packages for much of the underlying logic. So when you're using Spatial AI in OML4Py and you create one of these models and apply a method to look at some summary of the model and model statistics, you're going to see a bunch of results that would look very familiar if you work with some of these well-known libraries that you load and configure yourself. Because we're just, in many cases, integrating them, having them integrated and ready off the shelf. So anyone that works with these things, it's going to be, it's going to be the spatial error model that you know and love, so to speak, but within an easier environment, more scalable environment. The data behind the scenes is not a file from your laptop that you loaded with a cap on its, memory consumption. It's going to be a table in Autonomous Database.
All right, and yeah, real quick, another question was about vessel trip analysis and forecast. And I think it's probably on the roadmap, like you were mentioning, because it will have to be, it will have to do with the spatial temporal analysis,
That's it.
right?
That you're exactly right. And so that whole we'll say trajectory analysis and looking at spatial temporal data, looking at trajectories and all kinds of other factors that influence trajectories and making predictions of where do we think this ship is going to dock, sort of a thing. That is very much in the spatiotemporal realm and is absolutely something that have like work undergoing and well underway in addressing that trajectory prediction scenario. But that again is a roadmap. And it's very useful for us and it reinforces our effort to hear people asking about that because we are working on it. Okay, so yeah, all of those are great questions and appreciate it. So I want to, for the ADB-S, given this is sort of a ADB-S Learning Lounge, just to focus for a moment and put a little more of a fine point on this notion of these proxy data frames and ADB-S and all that. With OML4Py in general, you have data frames which point to tables. That's referred to as a proxy data frame. We do the same thing, but because in the realm of geospatial data and the nature of the geospatial ML workflows that we support, turns out that it's actually important for us to be able to support spatial data that is stored not only in ADB-S, but perhaps stored in object storage, or is stored in something called a geodata frame, which is a very popular way of structuring, well, a data frame people are used to working with, the sort of the standard way of working with data structures in Python. And there's a geospatial enhancement to that, pandas called geopandas, and a geodata frame is a very common way that people would want to work with geospatial data. So we want to make sure that we have like full support and full focus, and really the power and scalability and all the real horsepower comes from what we do with ADB-S. But we have the flexibility when appropriate and when it's useful for our API, for our algorithms, so forth, to point at geospatial data stored in other locations. So what I want to call out here is the fact that we have in Spatial AI, we have this spatial data frame, and that spatial data frame is our one object, which is this spatial data structure, and it is a proxy and pointing out to data wherever that data lives. And again, the focus and the real horsepower is when it lives in ADB-S. It might be a GeoJSON file in object storage, for example. Or it may be a shapefile that's been loaded into an attached volume in the OML4Py container, et cetera, et cetera. In all of those cases, you still have a spatial data frame that's a proxy that points to it. And when you apply one of our algorithms to it, like a clustering algorithm or something, it's going to leverage that data. There is one important thing though, and one real important value that I think is something that I referred to when I talked about that Python API for Oracle Spatial operations. When a spatial data frame is pointing to or is a proxy to data that is in ADB-S, then that operation sort of looks like this. So if I have a spatial data frame and that spatial data frame is pointing to a table in ADB-S, like I have a counties data, counties with demographics, that's a spatial data frame. If that spatial data frame is pointing and is a proxy to data in Autonomous Database, then if I perform a spatial operation like how many incidents, how many crimes crime locations are inside this county. If I perform a spatial operation like that, then as I mentioned before, we have this Python API for spatial operations. It would look something like this: my spatial data frame dot within distance. It's a Python, it's a method, and I can do that. Now, if the data is in ADB-S, as it in almost all cases, most cases would be, then what happens transparently behind the scenes is it becomes the spatial query that we see underneath. And that is what is actually invoked by the database. And the value there is that means that the horsepower behind these spatial operations is not sort of the ceiling of your what's in the how much memory is in your Python engine. It's a spatial query run in Autonomous Database. It's very, very powerful and scalable. And you as an OML4Py data scientist don't need to know what select SDO within distance. You don't need to know that table join structure and the predicate and all that. You're just applying a method to a spatial data frame. Now that's the case when all of the data involved in the operation, in this case, this operation would involve two spatial data frames. The data frame that like, counties, and another data frame that might be like crime incidents. And I want to know which crime incidents are within a distance of a county or something. When all that data is in the database, you end up with, behind the scenes, unbeknownst to you, running a spatial query in ADB-S. If some of this data is living and stored in another location, then of course we're not doing that. And that may be, for some reason, something that's useful in other occasions to have some of the data here, some of the data there. We can still run the algorithms and apply the methods. But the big point here for ADB-S is that when all this is focused in the database, you're really using the horsepower of the database, not just to store the data, but to actually invoke backend operations. So I want to show some examples of what some of these sort of fundamental steps look like in notebooks, and then I'll jump back into a live thing at the end. So a couple of quick examples, and the scenario and what the examples primarily involve is data, actually the same data that's used in the sample notebooks that I started out with. And that's data that is data from the US Census Bureau that has demographic information about people and income and home values and all that sort of stuff. And it's generalized, all this census data is generalized and aggregated and summarized to some summary level. And they have, the census has a hierarchy of these geographic areas that they use for those summaries. And one of those levels of this geographic hierarchy is something called their block groups. So they have blocks, these little tiny areas of just a few blocks. Then they assemble those into these larger block groups and up into tracks and so on and so forth. So this data set that I'm showing is a bunch of spatial data that has the shape of these block groups. And within each of those areas, a bunch of demographic data. And that's obviously useful for a variety of machine learning exercises. So that's sort of the scenario. So the first thing is, what does it look like to access that data from OML4Py using Spatial AI? So here I have an example of this thing I've kept talking about, SpatialDataFrame, and the fact that it might be pointing to or proxy to data that's in object storage or in one place or another. Well, in this case, you see in red, I'm creating a spatial data frame, and it is a database data set, DB spatial data set. And so all I'm doing is saying, here's the name of the table, create a spatial data frame. I now have a spatial data frame, a very familiar construct in Python, and it is simply a proxy to a table, spatial table in the database. And I can see the columns, I can see actually see the geometry that defines that block group shape. So that's having created a block group. Now maybe I want to explore the data and look at some spatial relationships. Well, I've got a spatial data frame of school locations, just a table in the database that I previously created a spatial data frame for, and the one that I just showed, so a spatial data frame for those block group areas. And I'd like to know, I'd like to identify which schools are within 2 kilometers of a particular block group, just sort of an ad hoc example of exploring the data for some spatial relationships. So ADB sort of database people would look at this and say, oh, it's doing SQL. That's a within distance query. You can do that very easily. But the persona here is not a database developer. The persona here is, this is a data science workflow in a Python notebook. Therefore, I'm just going to apply a method to my school's data frame. I want to know which ones are within a certain distance of a block group. I'm going to apply this within distance method that we have on our spatial data frame and identify the schools within that distance of 2,000 meters of a particular block group. I never need to know or care about the fact that when I click the go button, select blah, blah, blah from, SDO within distance equals true, all that stuff. I don't care. I don't know. I just know that I could apply a Python method to my data frame and get a spatial query result. And that sort of thing becomes useful for feature engineering that involves a spatial calculation. So we call that like spatial feature engineering. I want to add a new feature or column to my data that might be useful for predictions. And that column is going to be based on some spatial operation. In this case, I want to add a new column to my demographic data. And I want to know for each of these block groups, how far is the nearest school? Because if I want to predict something like the value of a home in a block group, for example, then it might be helpful in the predictive sense to know how far is the nearest school from that block group, just as an example. So that API I just showed comes into play here. So now I've got a spatial data frame of schools, and I can apply this nearest neighbor operation to it and some aggregating and summarizing. And the point here is at the end, I can then have a result that is added as a new feature, distance to nearest school in meters. Now that is just a new feature, or in the ML, ML would talk about features, and database people would talk about columns, but that's just another sort of attribute that is potentially of value in training a predictive model. So that's this is sort of pre-processing stuff. And another example of pre-processing stuff is I talked about gap filling before. And filling gaps in data is an algorithm that's referred to as imputing, or imputation is filling missing data. And the algorithm that fills missing data is an imputer. So generally speaking, if you would fill missing data using an algorithm that would look at if the column has missing, or if a feature has missing values, you would take some statistical average of the non-null data and use that to fill the missing values. Well, in this case, we're filling missing values using location-specific surrounding values, so that the values that are missing are filled with values that are that are appropriate for the spatial context of that missing value. So when we're replacing a missing value in a location, we're going to take a statistical aggregate or summary of all the nearby surrounding values. Now, doing that makes some assumptions about whether it's appropriate to say that I'm going to fill a missing value for average education level or something like that. Is that appropriate to fill that missing value with a summary of nearby values? Well, part of what we have in spatial AI are the algorithms that will determine whether that is a good assumption. They will determine whether something like median income at a location, they'll determine whether it is positively correlated with its neighbors, so that you know whether a particular variable or feature can be safely filled with surrounding neighbors' values. Here's an example of applying a clustering algorithm, just a DB-scan clustering algorithm that is a spatial algorithm. So DB-scan is a common clustering technique, common clustering algorithm in the spatial realm that is sort of applied to clustering, where you're specifying how near neighbors items have to be considered part of a cluster. You have different thresholds, and then you label data. In this case, we see colors representing labels of items that have been detected to be car crashes that are part of the cluster. And then finally, I think this is the one I showed at the beginning, other algorithms like detecting hotspots and cold spots. So unlike clusters that have to do with sort of the density of features, lots of occurrences of something like crimes or crashes that are all clustered close to each other, hotspots and cold spots are different. That's looking at some attribute like income or unemployment, or something that exists sort of to some degree everywhere across all zip codes or counties or what have you. And hotspots and cold spots is an algorithm that allows us to determine what are the areas that have a relatively elevated or depressed level of whatever that feature is that you're interested in. So here maybe these are hotspots and cold spots of average income across those census block groups. So this is just some examples of what spatial AI provides and what it looks like within a notebook. I will mention quickly that included are a whole bunch of different regression algorithms, prediction algorithms, and those different prediction algorithms are designed to designed to address different scenarios, like I mentioned at the beginning, different scenarios in the data. What type of spatial effects are do the data exhibit? And we have, and this is one example of that, we have algorithms that will sort of introspect and look at the data, look to see what spatial effects are inherent in the data, and then give you back the statistics, and in this particular case, an actual suggestion of what spatial algorithm is best suited to address those spatial effects. And then you sort of then have a clue into, okay, this is the model that's going to perform best or give me the best improvement over a non-spatial model, given the spatial effects that are observed in the data. And I'm rapidly running out of time, I think, so I just want to provide a couple of takeaways, and then maybe I'll be able to take a minute or two and show a couple of other things. But really, the big takeaways here are that what we're talking about are just a new set of capabilities in OML4Py and ADB-S. It's nothing different that you install or configure or license or anything. It's all about algorithms and features that address and take advantage of location and location effects within your data. That's both algorithms to predict and detect, but also pre and post processing. And that also includes the ability to perform sort of some essential spatial operations using Python without having to know the underlying SQL. So I want to take just a minute here to jump back and show a couple of quick things. So if we go back to the set of examples, I showed just opening one of these examples, but if you go to any example of interest in here, for example, maybe one of these spatial regression notebook examples, instead of clicking on the link, if you click in the gray area and highlight it, you can then click Create Notebook, and it will make a copy of it into your own project that you can then play around with. And I did that a little bit earlier and copied one of the Spatial AI sample notebooks for detecting outliers. So folks asked earlier about whether these are algorithms that we created or whether they're algorithms that are sort of industry standard. Well, this is a standard. LOF stands for local outlier factor. We didn't invent that. That's a very well-established algorithm. So spatial outlier algorithm is going to use some thresholds that you set, and then it's going to basically return a score for data and that score or that label is the degree to which that observation is an outlier. So the higher the score that this returns, the more confident that we are, the more of an outlier that it is. So a very small LOF, it's not really an outlier. The bigger the LOF, it's an outlier. So in this particular sample, we're using car crashes, and I showed you sort of the end result of that for doing clustering, but this is now looking for outliers. So we create one of those spatial data frames, just pointing at a table in ADB of accident data. And then I end up just sort of doing some exploration to sort of understand what the attributes mean. And I decide I want to just look for outliers for crashes that involve serious injury, not just little fender benders. So I look at the data and figure out how to just get those crashes that involve serious injury. And this is really the part that's important. I then apply, so I've got a data frame that are now just the serious injury crashes. And what I want to do is I want to apply that local outlier factor spatial algorithm to the data. And then I can look at the distribution of labels that are created. And as expected, most of the data have a very low outlier factor. They're not really outliers, but a few of them you can see have a high outlier factor. Those are the outliers. And I'm going to say that an outlier factor greater than 1.5 is an outlier. So then I can just look at that labeled data and plot it, and I can see here the data labeled. So now these are all the crashes, and the ones that are in red are the ones that the spatial outlier algorithm has determined are outliers. And that's all based on thresholds that can be adjusted, but this is what sort of a first cut does. And then another standard sort of thing that is done with something like this outlier detection is not just to look at an existing data set and find the outliers in it, but to use that existing data set to train a model that will then, you can then feed new locations to, And as those new locations come in, tell me right then and there, is this an outlier? Is this an outlier? And that's referred to as novelty detection, not just a given data set, find the outliers, train a model based on a data set that has normal and outlier data, and then detect outliers in new data. So here's doing that. So we've got the same local outlier factor. This time I want to do this for novelty is true. In other words, I want to train this for detecting outliers in new data. And then just to test the result, I'll have a bunch of random coordinates. This is literally just, based on doing creating random points within the area of interest, and then apply that train model to it and label which ones does it think is an outlier and which one does it think is not an outlier. And here's the result. So in gray are all of the original crashes that were used before to train the model. Some of the gray ones are outliers at the edge, some of them are not. The new data, the novelty data, is the data that's in red and green. That's what I just fed in as brand new data. And it's telling me of that brand new previously unseen data, the ones in green are normal, the ones in red are outliers, and it does a pretty good job. So that's something that would be like a data feed, and you want to know as things are coming in, you want to have some alert when some new data represents some geospatial anomaly or outlier. So that's sort of the one example, I have time to show, and I'm actually a minute over. But remember that there are all those other sample notebooks, and also I will close just by putting up on the screen these links that I think can be probably put into the chat so people know where to look for the documentation. And I think, Marcos, that's all the time that I have, and I appreciate the opportunity.
Thank you very much. Yeah, no, it was great, David. Yeah, really, really interesting. There were several questions that were already answered. The other ones that you did already, right, previously. So again, thank you very much. If you can put the links in chat for everyone to see, that's going to be great. I'm going to distribute those links afterwards as well for the folks with the recording. So thank you, guys. I'm going to put some of these links again for the Autonomous Database links. You guys can always go there, and we're going to point you guys to the Spatial AI features there as well. Again, thank you very much for joining us today, guys. Again, please come back to the Learning Lounge in the future. We're going to have the session and recording, and in here where you see it in the screen, we're going to have upcoming sessions there. Right now, you're going to see that there is a Spatial in Spanish next week, and the week after we're going to do one in Portuguese. And then the recordings are all there as well, right? So when you go back to the recordings, you're going to find the links to the slides, and then the information that David gave, the links are going to be there as well, okay? All right. So again, thank you very much for joining, guys. It was great. Really appreciate it, David. I'll leave some music playing right now in the background while I do expect any other questions. You guys have other questions, you can type them in. We're going to get back to you, okay? So, all right. So really appreciate it, David. Thank you very much.